Before getting into this, it's worth being upfront about something. Nothing James Webb has found on Saturn is actually terrifying. There's no danger, no threat, nothing remotely resembling the kind of story that word usually implies. But there is something genuinely intense happening at Saturn's North Pole, something with a scale and a self-perpetuating power that, once you understand the actual physics involved, earns the word intense far more honestly than a manufactured scare ever could. In May 2026, using data gathered by the James Webb Space Telescope, a team of astronomers finally confirmed the existence of a real physical engine running continuously at Saturn's pole, an engine powered entirely by the planet's own aurora, generating winds, electrical currents, and enough heat to solve a genuine, more than 2-decade-old scientific mystery about how this entire gas giant actually behaves. This is the real story of what James Webb actually revealed about Saturn, the genuinely extreme physics driving its polar regions, and why the researchers who found it describe the underlying mechanism as something closer to a planetary heat pump than anything resembling the calm, quiet aurora displays we're used to seeing here on Earth. I'm your host, and this is your channel. If you want the real science behind the biggest discoveries in space, subscribe now, because we're just getting started. To understand why Saturn's aurora represents something genuinely more extreme than anything happening in our own planet's atmosphere, you first need to understand the basic physics behind how auroras form in the first place, and then understand exactly how dramatically Saturn's version of this phenomenon differs from Earth's. On our own planet, auroras occur when charged particles, streaming outward from the sun, carried by the solar wind, collide with Earth's magnetic field and get funneled down toward the poles, where they slam into gases in our upper atmosphere, energizing them and causing them to glow in the shifting, colorful curtains of light we know as the northern and southern lights. It's a genuinely beautiful phenomenon, but by cosmic standards, it's a comparatively modest one, driven primarily by activity happening 93 million miles away on the surface of our sun, and largely absent whenever the sun itself happens to be quiet. Saturn's aurora operates on a related but dramatically more extreme set of physical principles. Saturn possesses by far the strongest planetary magnetic field of any world in our solar system, generated deep within its interior by the churning motion of liquid metallic hydrogen under crushing pressure and extending outward to form an invisible magnetic bubble called a magnetosphere, so large that if it could somehow be made visible in Earth's own sky, it would appear several times wider than the full moon. That magnetosphere doesn't just deflect the solar wind the way Earth's does, it actively traps and accelerates charged particles within it, holding onto them and cycling them through the system continuously rather than simply letting them pass by. And Saturn's aurora draws energy not just from the solar wind, but from an additional internal source most other planets simply don't have. Charged particles supplied continuously by its own moons, particularly the small icy moon Enceladus, whose active geysers constantly spray water vapor out from cracks near its south pole into the surrounding space environment. That water vapor doesn't simply drift away and disappear. Exposed to solar radiation and to the intense particle environment surrounding Saturn itself, the water molecules gradually become ionized, stripped of electrons, transforming into charged particles that get swept up by Saturn's rotating magnetic field and dragged around the planet at tremendous speed, effectively feeding a constant, self-replenishing supply of raw material directly into Saturn's already ferociously energetic magnetic system. Some of that material eventually forms Saturn's E-ring, a faint, diffuse band of ice particles that traces Enceladus' own orbital path around the planet, while a considerable portion gets pulled inward, adding to the dense cloud of charged particles, or plasma, that Saturn's magnetosphere continuously drags along with it as the planet spins. The combined result of all this, the strongest magnetic field in the solar system continuously fed by both the distant sun and an active, geologically alive moon, is an aurora that is, by any reasonable measure, hundreds of times more energetic than anything Earth ever produces. A genuinely extreme, continuously active phenomenon playing out at the pole of the second largest planet in our solar system, dwarfing the comparatively gentle intermittent light, shows most people on Earth associate with the word aurora entirely. For more than 2 decades, this same general region of Saturn's polar magnetic environment had also been at the center of a genuine, unresolved scientific mystery, one that, on its face, sounded almost impossible. Beginning with observations made by NASA's Cassini spacecraft starting in 2004, scientists noticed something that violated basic planetary physics. Saturn's measured rotation rate, determined by tracking specific radio signals tied to the planet's magnetic field, appeared to be gradually changing over time, drifting by minutes across the course of Cassini's mission, as though the entire planet were somehow speeding up and slowing down its own spin. Planets simply do not do this under ordinary circumstances. A world's fundamental rotation, established during its original formation billions of years ago, should remain essentially fixed unless something catastrophic happens to it. And nothing catastrophic had happened to Saturn. It's worth understanding exactly why measuring Saturn's rotation rate at all requires this kind of indirect, radio-based technique in the first place, because that underlying difficulty is really the root of the entire multi-decade puzzle. Saturn, like every other gas giant, has no solid surface, no fixed geographic landmark. Astronomers could simply watch complete one lap and call a rotation period. Its visible cloud bands drift and shift at different speeds depending on latitude, a phenomenon called differential rotation, meaning you can't use the clouds themselves as a reliable stand-in for the planet's true underlying rotation rate either. Astronomers instead had to rely on tracking periodic radio emissions generated deep, within Saturn's interior, signals tied directly to the planet's rotating magnetic field, on the theoretical assumption that this magnetic field is rigidly anchored to Saturn's actual internal rotation, and would therefore provide a reliable, consistent proxy for the true spin rate, hidden far beneath the visible cloud tops. That assumption had worked reasonably well for NASA's earlier Voyager spacecraft, which flew past Saturn in 1980 and 1981 and used exactly this radio tracking method to establish an initial estimate for the planet's rotation period. But when Cassini arrived at Saturn in 2004 and began its own long-term monitoring campaign, its measurements of that same radio signal produced a puzzlingly different rotation period than Voyager had measured a quarter century earlier. And worse, Cassini's own measurements kept shifting further over the course of its own 13-year mission, refusing to settle into any single, stable, consistent value. NASA's own mission documentation on Cassini's study of Saturn's magnetosphere described this specific outcome plainly, noting that the planet's rotation rate remained a genuine mystery, and that Cassini showed it to be far more complicated than anyone had originally expected, since an actual physical slowing or speeding of Saturn's genuine internal rotation was considered highly unlikely given everything else known about planetary physics. Scientists understood almost immediately that something else, some other physical process entirely, had to be responsible for the strange, shifting readings, even though pinning down exactly what that process was would ultimately take more than 20 years of dedicated incremental research to fully resolve. The first genuine breakthrough in solving this puzzle came in 2021, when a research team led by Professor Tom Stallard of Northumbria University proposed a compelling alternative explanation. Saturn's actual rotation, the team argued, hadn't changed at all. What had changed were the electrical signals scientists were using as an indirect proxy for that rotation, signals tied to the planet's aurora, and those specific signals were being distorted by powerful winds blowing through Saturn's upper atmosphere. In other words, the planet itself was stable. The measurement had been misleading everyone, thrown off by an entirely separate atmospheric process nobody had properly identified yet. That explanation resolved the most physics-defying part of the mystery, but it immediately opened a second, equally pressing question. What was actually generating those powerful winds in the first place? Winds don't simply appear from nothing, and answering that question required a level of detailed atmospheric measurement that no instrument available at the time could actually provide. It's worth pausing here to note that this rotation puzzle wasn't the only genuinely strange finding to come out of Cassini's long 13-year study of Saturn's magnetic environment. During the mission's final months, as Cassini executed its so-called grand finale, a series of daring dives directly through the narrow gap between Saturn's cloud tops and the inner edge of its rings, the spacecraft's magnetometer team, led by Professor Michael Dougherty of Imperial College London, discovered something else that genuinely puzzled scientists. Saturn's magnetic field showed no discernible tilt, relative to the planet's own rotation axis at all. That might not sound alarming on its own, but it directly contradicted a basic theoretical principle scientists had relied on for decades. The belief that generating a planetary magnetic field in the first place requires some meaningful tilt between a planet's rotation axis and its magnetic axis in order to sustain the internal electrical currents responsible for producing the field to begin with. Dougherty herself described the finding as challenging in blunt terms, noting that the tilt seemed to be much smaller than anyone had previously estimated, and quite difficult to explain using existing theory. That specific puzzle, distinct from the rotation rate mystery but tangled up with it in the broader effort to understand Saturn's magnetic behavior, remains only partially resolved even today, part of the same broader, decades-long project of understanding exactly how this planet's magnetic environment actually works. That's exactly the gap James Webb was uniquely equipped to help close, at least with respect to the specific rotation rate puzzle. It's worth appreciating exactly how large and how genuinely international the research effort behind this final breakthrough actually was, because a discovery this significant rarely comes from a single lab working in isolation. Stallard's team drew together researchers spanning 8 separate institutions: Northumbria University, where Stallard himself is based, along with Boston University, the University of Leicester, Aberystwyth University, the University of Reading, Imperial College London, Lancaster University, and the Johns Hopkins University. Applied Physics Laboratory in the United States. That kind of broad, multi-institutional collaboration reflects just how many different areas of specialized expertise a project like this genuinely requires. Atmospheric modeling, magnetospheric physics, infrared spectroscopy, and the practical engineering knowledge needed to actually plan and execute a technically demanding, sustained observation using one of the most oversubscribed scientific instruments ever built. The research was funded through the UK's Science and Technology Facilities Council, and the full findings were published under the formal title JWST/NIR spec reveals the atmospheric driver of Saturn's variable magnetospheric rotation rate, appearing in the Journal of Geophysical Research, Space Physics, in its third 2026 volume. Stallard, working alongside that full team of collaborators, turned Webb's instruments towards Saturn's northern auroral region and observed it continuously for an entire Saturnian day, an unbroken observation window that gave the team a level of detail no previous instrument had ever achieved for this specific part of the planet. The team focused their observations on infrared light emitted by a molecule called trihydrogen cation, sometimes written as H3+, which forms naturally in Saturn's upper atmosphere when energetic particles from the aurora collide with and ionize ordinary molecular hydrogen. This particular molecule turns out to be an unusually useful diagnostic tool for planetary scientists, because the specific pattern and intensity of the infrared light it emits changes in a well-understood, predictable way depending on the surrounding temperature, meaning that carefully mapping H3+ emission across a region of a planet's atmosphere effectively lets researchers build a detailed thermal map of that region without needing to physically measure temperature by any more direct means. The same molecule and the same basic technique have become genuinely important tools across outer planet atmospheric research more broadly, since it's one of the few reliable ways to study upper atmosphere temperature structure on a planet no spacecraft could ever practically land on or sample directly. By mapping exactly how this molecule's glow varied across the auroral region, the team produced the most detailed temperature and particle density maps ever assembled for this part of Saturn, achieving roughly 10 times the precision of any earlier measurement technique. To put that improvement in concrete terms, earlier instruments carried uncertainties of roughly 50 degrees Celsius in their temperature measurements, an error margin large enough to completely obscure any subtle, localized variation in heating across the auroral region. Webb's far greater precision finally allowed researchers to identify specific, localized patterns of heating and cooling that had simply been invisible to every previous instrument, distinguishing genuinely hot pockets of atmosphere from cooler surrounding regions with a level of spatial detail nobody had achieved before. What that data revealed, once compared against theoretical models built more than a decade earlier, confirmed a genuinely elegant and self-sustaining physical process, one with a scale and intensity worth sitting with directly. Energy deposited by the aurora heats specific, concentrated regions of Saturn's atmosphere. That concentrated heat generates powerful winds. Those winds, moving through Saturn's magnetized upper atmosphere, generate electrical currents, and those currents loop back to help power the aurora itself, continuing to heat the atmosphere and sustaining the entire cycle indefinitely, an ongoing feedback loop that requires no external trigger to keep running. A real physical engine that has apparently been operating continuously at Saturn's pole for as long as anyone has been watching. Stallard's own description of this mechanism captures the genuine intensity of what's actually happening there. What we are seeing, he explained, is essentially a planetary heat pump. Saturn's aurora heats its atmosphere. The atmosphere drives winds. The winds produce currents that power the aurora, and so it goes on. The system feeds itself. He described the broader arc of the investigation directly as well. For decades, researchers knew something strange was happening with Saturn's apparent rotation rate, but couldn't explain it. The team then showed it was being driven by atmospheric winds, but still didn't know why those winds existed. These new observations, made possible specifically by Webb, finally gave the team the evidence needed to close that loop entirely. It's worth taking a moment to compare this specific self-sustaining mechanism against what researchers already understood about Jupiter's own separately studied aurora, because the comparison helps illustrate exactly how genuinely unusual and genuinely significant Saturn's particular feedback cycle actually is. Jupiter's aurora is, by most measures, the single most powerful and most energetic auroral display anywhere in our solar system, driven by an even stronger magnetic field than Saturn's, and fed by its own volcanically active moon, Io, whose sulfur-rich volcanic plumes contribute an even larger, more continuous supply of charged particles than Enceladus provides at Saturn. Researchers have spent decades studying Jupiter's aurora in detail, and while it shares some broad similarities with what Webb has now confirmed at Saturn, energetic particles funneled toward the poles, significant atmospheric heating in the auroral zones, real interaction between the atmosphere and the surrounding magnetosphere. Jupiter's system operates at an even more extreme scale, and researchers have not yet established with the same level of confirmed, detailed physical evidence exactly how completely self-sustaining its own heating wind current cycle actually is, compared to what Stallard's team has now specifically demonstrated for Saturn. That distinction matters because it means Saturn, despite being the less extreme of the two systems in raw energetic terms, has actually become the better understood example of exactly how this kind of self-sustaining planetary engine works in physical detail, precisely because Webb's specific sustained observation campaign targeted Saturn's aurora with a level of continuous, high-precision coverage that hadn't previously been applied to either planet's polar regions. There's also a genuinely intriguing forward-looking implication buried in Stallard's own comments about what this discovery might mean beyond our own solar system entirely. When he described the finding as changing how researchers think about planetary atmospheres more generally, he was pointing toward a research question that extends well beyond any single planet. If a world's atmospheric conditions can genuinely drive electrical currents flowing out into the surrounding space environment, then any planet, anywhere, with the right combination of a strong internal magnetic field, sufficient rotational speed, and either a nearby star's stellar wind or some internal particle source comparable to Enceladus or Io, could, in principle, host a broadly similar kind of self-sustaining auroral engine. That's a genuinely significant consideration for researchers studying exoplanets, planets orbiting other stars entirely, because it suggests that auroral activity and its associated atmospheric heating could represent a much more universal, much more energetically important process across giant planets throughout the galaxy than researchers had previously appreciated, rather than being some kind of unusual, specifically local quirk of our own solar system's particular planets. It's worth understanding just how significant this finding is beyond simply resolving one planet's measurement puzzle, because the research team has been direct about its broader implications for how scientists think about giant planets generally. The study found genuine, direct evidence that Saturn's atmosphere and its magnetosphere, the vast surrounding region of space shaped by the planet's own magnetic field, are far more tightly interconnected than researchers had previously appreciated. An ongoing two-way exchange of energy that likely explains why this entire self-sustaining cycle has remained so stable for so long. Stallard connected the finding to a genuinely broader scientific principle. This result, he said, changes how researchers think about planetary atmospheres more generally. If a planet's atmospheric conditions can drive currents out into the surrounding space environment, he explained, understanding what's happening in the stratospheres of other worlds may reveal interactions we haven't even imagined yet. There's a reason this kind of intense, self-sustaining electrical and thermal system deserves genuine attention rather than manufactured drama, and it comes down to scale. Saturn's aurora sits at the pole of a planet roughly 95 times the mass of Earth, drawing on a magnetic field vastly stronger than our own, fed continuously by charged particles supplied both by the distant T-sun and by an active, geologically alive moon spraying water vapor into space. The resulting system generates genuinely extreme temperatures, genuinely powerful winds, and genuinely significant electrical currents, all cycling continuously, self-sustaining, at a scale that dwarfs anything happening in Earth's own comparatively gentle polar regions. That's not manufactured fear. That's simply what real planetary physics looks like. When you scale it up to a world this large, with an energy source this powerful, and it's precisely the kind of genuine intensity that makes Saturn worth studying closely, rather than needing to invent something frightening about it. It's worth sitting with the sheer physical scale of the currents involved here for a moment, because it's genuinely difficult to picture. The electrical currents generated by this self-sustaining cycle don't stay confined to a small, localized patch of atmosphere. They flow along Saturn's magnetic field lines across enormous distances, connecting the planet's upper atmosphere to its broader magnetosphere, a structure so large that Saturn's entire magnetic bubble, if you could somehow see its full outline from Earth, would stretch across a region of space larger than the Sun itself. Currents of this scale, self-sustaining and continuously replenished by the very aurora they help power, represent one of the most energetically active, continuously operating systems anywhere in our own solar system. A genuinely planet-sized electrical engine that has, according to the best available evidence, been running in some form for as long as Saturn has possessed both its magnetic field and its geologically active moon. This spin mystery research connects to a broader, genuinely sustained pattern of Webb-based aurora studies across the outer solar system, part of a systematic, multi-year effort by overlapping teams of researchers to understand how magnetic fields, atmospheres, and auroras interact across every one of the giant planets, not just Saturn. Understanding why this broader campaign matters requires appreciating that each giant planet's magnetic environment is genuinely, meaningfully different from the others, shaped by that planet's own specific combination of internal structure, rotation speed, axial tilt, and the presence or absence of geologically active moons feeding material into its magnetosphere. Around this same general period, a separate team led by Dr. Henrik Mellon of the University of Leicester turned Webb's instruments toward Uranus, a planet whose auroras represent one of the strangest cases anywhere in the solar system. Unlike every other major planet, Uranus rotates almost entirely on its side, tipped over by roughly 98 degrees relative to its orbital plane, likely the result of some ancient catastrophic collision early in the solar system's history. That extreme tilt carries over into its magnetic field as well, which sits tilted a further 60 degrees relative to the planet's own rotation axis, an already strange configuration layered on top of an already strange planetary orientation. The practical result is that Uranus's auroras don't behave the way auroras do on any other planet astronomers have studied. Rather than forming neat, concentrated rings around the geographic poles the way Earth's, Jupiter's, and Saturn's auroras generally do, Uranus's auroras extend across a much broader swath of the planet, positioned around its magnetic poles rather than its geographic ones, producing genuinely widespread auroral activity that one researcher involved in the study described as one of the strangest auroral displays anywhere in the solar system. Webb observed Uranus continuously across a full Uranian day, roughly 17 Earth hours, in January 2025, successfully mapping the vertical structure of the planet's ionosphere and its auroral bands in 3 dimensions for the first time in the history of Uranus research, a genuine milestone for a planet whose auroras had only been tentatively confirmed at all as recently as 2022. Separately, Webb also detected auroral activity on Neptune for the first time in the telescope's own operational history, extending the same broad research program to the outermost of the solar system's giant planets, a world so distant and so faint that even confirming the existence of auroral activity there at all required Webb's specific combination of sensitivity and infrared capability. And this entire body of Saturn and ice giant research sits alongside an even longer-running parallel effort studying Jupiter's own famously powerful auroral displays, the most energetic and most extensively studied aurora anywhere in the solar system outside of Saturn's, driven by a similar combination of an extraordinarily powerful magnetic field and a steady supply of charged particles fed by Jupiter's own volcanically active moon, Io, which plays a broadly similar role in Jupiter's system to the one Enceladus plays at Saturn. Taken together, this systematic cross-planet research program has begun revealing a genuinely important pattern. Auroras throughout the outer solar system are not simply smaller or larger versions of Earth's own northern and southern lights, scaled up or down according to a planet's size. They're shaped by an entirely distinct set of physical relationships specific to each individual world, its magnetic field strength and orientation, its rotation speed, its axial tilt, and critically, whether or not it happens to have a geologically active moon feeding a steady supply of charged particles directly into its magnetosphere. Saturn and Jupiter, both fed by active moons, produce genuinely extreme, energetically self-sustaining auroral systems, unlike anything Earth experiences. Uranus, lacking that kind of internal particle source but possessing its own uniquely strange magnetic geometry, produces auroras that behave in an entirely different, still poorly understood way. Understanding these differences in detail, planet by planet, is precisely what this entire multi-year Webb research campaign has been working to establish. It's worth spending a little more time specifically on Enceladus' role in all of this, because the connection between a small icy moon and the extreme electrical activity happening at Saturn's distant pole is genuinely one of the more elegant relationships in solar system science. Enceladus itself is tiny, just over 300 miles across, easily overshadowed by Saturn's much larger and more famous moon titan. But since Cassini first discovered its plumes in 2005, jets of water vapor and ice erupting from cracks near its south pole, informally nicknamed tiger stripes, scientists have come to understand that this small moon plays an outsized role in shaping the entire environment surrounding Saturn. The water vapor escaping from Enceladus doesn't simply vent away into nothingness. A portion of it falls back onto the moon's own surface, some of it escapes to form Saturn's diffuse E-ring, tracing Enceladus' orbital path around the planet, and a meaningful fraction becomes ionized by solar radiation and the intense particle environment surrounding Saturn, transforming into charged plasma that gets swept up by Saturn's powerful, rapidly rotating magnetic field. That process effectively makes Enceladus into a continuous particle generator for Saturn's entire magnetosphere, constantly replenishing the supply of charged material available to be accelerated, funneled toward the poles, and ultimately deposited into the atmosphere as part of the aurora. Without Enceladus's ongoing contribution, Saturn's magnetosphere would likely still generate some aurora, driven purely by the solar wind the way Earth's does, but it would almost certainly be a dramatically weaker, less energetically self-sustaining system than the one Webb actually observed. Andrew Coates, a professor of physics at University College London, who has separately studied how Saturn's rapid rotation and Enceladus's plasma output distort the shape of the planet's overall magnetic field, has described this general dynamic directly, explaining that Enceladus itself functions as a key driver of the entire surrounding space environment, releasing huge amounts of water vapor that gets ionized, loading the magnetosphere with heavy plasma that then gets pulled around as the planet spins. That broader body of research, while conducted using different Cassini instruments and published separately from Stallard's team's aurora work, points toward the same underlying conclusion from a different angle. Enceladus isn't simply an interesting, geologically active moon sitting somewhere within Saturn's system. It's an active, ongoing participant in shaping the physical behavior of the entire planet's magnetic environment, from the detailed structure of its magnetosphere down to the specific, self-sustaining electrical engine, now confirmed to be running at its pole. That connection carries real, practical significance for future exploration as well, beyond simply being an elegant piece of physics. As space agencies begin developing serious plans for potential future missions to return to Saturn and specifically to Enceladus, missions aimed at searching more directly for signs of life within the moon's hidden subsurface ocean, understanding exactly how energetic and how electrically active the surrounding Saturnian environment actually is, becomes a genuinely practical engineering concern, not just a scientific curiosity. A spacecraft designed to operate for extended periods within this kind of energetically extreme magnetic environment, cycling through powerful, self-sustaining electrical currents and bombarded by charged particles accelerated to significant energies, needs to be engineered with that specific environment in mind, and research like Stallard's team's aurora study provides exactly the kind of detailed, physically grounded understanding that future mission planners genuinely need. This isn't a purely theoretical concern either. Enceladus has, over the past several years, become one of the single most compelling targets in the entire search for life beyond Earth, following a series of discoveries built on archival Cassini data showing that the moon's hidden ocean contains phosphorus at concentrations far exceeding Earth's own oceans, along with complex organic molecules confirmed to originate from active chemistry happening directly within that ocean. That accumulating body of evidence has fueled real, growing momentum within the scientific community for a genuinely dedicated follow-up mission, one specifically built to search for direct signs of life within Enceladus's ocean, rather than simply cataloging its chemical building blocks, the way Cassini's more general purpose instruments were able to. Any such mission, however it's ultimately designed, will need to operate for an extended period somewhere within the same energetic Saturnian environment that Stallard's team has now mapped in unprecedented detail, and every additional piece of physical understanding about exactly how that environment behaves, how strong its currents are, how energetic its particle populations get, and how all of that activity connects back to the planet's own magnetosphere directly improves the odds that a future mission can be engineered to survive and operate successfully there for as long as its scientific goals require. It's worth being honest and precise about exactly what this research represents and what it doesn't, because that precision is what separates a genuinely compelling scientific story from an exaggerated one. Nothing about Saturn's aurora, however intense and energetically extreme it genuinely is, poses any threat to Earth or to any spacecraft studying it from a safe orbital distance. The intensity here is a matter of scale and physics, not danger. James Webb itself observed this entire phenomenon from a position roughly 1 million miles from Earth, in the opposite direction from Saturn entirely, studying the planet's aurora from a distance of hundreds of millions of miles using nothing but the light Saturn's own atmosphere emits, with no proximity, no direct exposure, and no conceivable pathway by which anything happening at Saturn's pole could meaningfully affect anything here at home. Even Cassini, which spent 13 years flying directly through parts of Saturn's magnetosphere and, during its final grand finale orbits, dove repeatedly through the narrow gap between the planet's cloud tops and its innermost rings, encountered nothing from this energetic environment that threatened the spacecraft beyond the ordinary, well-understood engineering challenges of operating a spacecraft that close to a giant planet's own magnetic field for an extended period. What makes this discovery genuinely remarkable is the sheer elegance and self-sustaining power of the mechanism itself, a real, continuously operating planetary engine, confirmed through the years of patient incremental scientific work stretching from Cassini's original puzzling measurements in 2004, through Stallard's team's crucial 2021 reinterpretation, and finally to Webb's detailed 2026 confirmation of the underlying auroral heating process driving the entire cycle. That patient, decades-long arc from an initial, genuinely confusing anomaly in the data, through a partial theoretical breakthrough, to a final, detailed physical confirmation using an entirely different generation of telescope technology, represents exactly the kind of careful, cumulative scientific progress that rarely makes for a single dramatic headline moment. But that ultimately produces far more genuine, lasting understanding than any single, isolated discovery ever could on its own. It's also worth appreciating exactly what it actually took, operationally, to gather the specific dataset that finally solved this puzzle, because the observation itself represented a genuine feat of careful mission planning, not simply pointing a telescope and pressing a button. Observing Saturn's northern aurora continuously for an entire Saturnian day meant committing a substantial, uninterrupted block of Webb's extremely limited and highly sought-after observing time to a single, sustained target. A real trade-off, given how many other research teams across the world are simultaneously competing for access to the same telescope. That sustained observation window was essential precisely because auroral activity isn't static. It shifts and varies continuously as a planet rotates, as its magnetosphere responds to changing solar wind conditions, and as the underlying electrical currents driving the aurora wax and wane in intensity. A single brief snapshot, the kind of observation in many earlier studies of Saturn's aurora had been limited to, simply couldn't capture the kind of continuous, evolving picture the research team needed to actually trace the specific relationship between localized heating, wind generation, and current flow that the self-sustaining cycle depends on. The specific timing of the observation mattered too. Saturn's own seasons, driven by its axial tilt and its lengthy, roughly 29-year orbital period around the Sun, mean that different hemispheres receive dramatically different amounts of illumination, and, correspondingly, different levels of auroral activity depending on where the planet sits in its seasonal cycle at any given moment. The research team's observations captured Saturn's northern aurora during a period when that hemisphere was well illuminated and readily observable, giving researchers optimal conditions for capturing the kind of detailed, high-precision data the study ultimately depended on. So here is where this genuinely, honestly leaves things, based entirely on peer-reviewed research published in the Journal of Geophysical Research, Space Physics, and the direct, on-the-record statements of the researchers who conducted this work. James Webb revealed in genuine, unprecedented detail a self-sustaining engine of heat, wind, and electrical current running continuously at Saturn's North Pole, powered by an aurora hundreds of times more energetic than anything Earth produces, fed by both the Sun and the planet's own geologically active moon, Enceladus. That discovery finally solved a genuine, more than two-decade-old mystery about Saturn's apparent rotation, tracing a puzzle that once looked like it violated basic physics, back to real, well-understood atmospheric processes, operating at a genuinely extreme scale. That is not manufactured drama built around an invented threat. That is the honest, carefully documented, genuinely intense reality of what's actually happening at the pole of the second largest planet in our solar system, confirmed through years of patient, collaborative scientific work. It's also worth noting what comes next for this specific research effort, because the team has been clear that this particular study, despite resolving the core rotation mystery, doesn't represent the final word on Saturn's auroral behavior. Researchers intend to continue monitoring Saturn's aurora using Webb and other available instruments as the planet's own slow, roughly 29-year seasonal cycle continues progressing, tracking how this self-sustaining heating and current system responds as Saturn's illumination gradually shifts from its current northern hemisphere favoring configuration toward its eventual southern spring and summer seasons in the 2030s. Comparing how the strength and behavior of this auroral engine changes as the underlying solar illumination conditions shift over years and decades should give researchers an even richer, more complete understanding of exactly how tightly this self-sustaining cycle is actually coupled to external factors like the solar wind versus how much of its behavior is driven purely by Saturn's own internal rotation and its steady supply of plasma from Enceladus, largely independent of anything happening on the Sun at all. So here is where this genuinely honestly leaves things, based entirely on peer-reviewed research published in the Journal of Geophysical Research, Space Physics, and the direct, on-the-record statements of the researchers who conducted this work.